The purpose of this video is to teach the steps involved in creating a basic assembly mechanism in Catia. The video will cover the tools and options in the Digital Markup Kinematics workbench, a step-by-step tutorial of how to make a mechanism, as well as some visual examples of some of the most useful joints and how they are used. This instructional video assumes a certain amount of experience with Catia, including skills in basic part design and basic assembly design, as taught in eTech 113. This video will demonstrate how to create a mechanism using parts that are already made. If you are following along with the video, you can find all the part files used in the examples located on the DVD inside of a zip file. Also, feel free to pause and rewind the video as needed while following the tutorial. Before beginning the tutorial, we will cover some simple safety considerations that can help make your Catia experience a positive one. While working at a computer might seem like a fairly safe, low-risk activity, there are several important considerations to keep in mind to ensure a pleasant and comfortable experience. The first consideration is that staring at a computer screen for extended periods can strain your eyes and cause aches in your head and neck. To avoid this, remember to keep the screen 20 to 40 inches away from your face, and make sure that it is at a distance that allows you to clearly see the entire screen without having to turn your head. Also, the top of the screen should be at or slightly below your horizontal line of sight, so that the entire height of the screen can be viewed without having to tilt your head up. In addition, the center of the screen should be located between 15 and 20 degrees below your horizontal line of sight. Be sure that your chair and seating position allow you to sit straight with your back supported and perpendicular to the ground, and make sure that your forearms are supported comfortably and are roughly parallel to the ground. These posture recommendations will help prevent discomfort and injury that can result from sitting for extended periods. Because working with Catia mostly involves lots of use of the mouse, be sure to take small breaks every once in a while to give your hand and wrist a rest from the repetitive movements. These breaks can also provide a good time to stand up and look away from the screen, stretch your legs, or walk around. There is one last consideration which concerns your mental health. It is not unheard of for Catia to sometimes crash or do strange things at very inconvenient moments. Because of this, it is important to save your work often to avoid potentially losing hours and hours of hard work. This simple recommendation can save you a lot of grief and mental anguish. For more information on safety recommendations regarding computers, you can visit OSHA's website and take a look at their page on computer workstations. Let's start with the basics. First, open Catia and activate the Dmu Kinematics workbench. From here, you can create parts just as you would in the assembly design workbench. In this example, we will import existing parts into the new product by selecting Insert Existing Component and choosing the necessary parts. The parts needed for this example are the handle and the base cat parts. Note that it is not necessary in this case to constrain all of the parts to each other, as they will become constrained as a mechanism is created. Once all the parts are inserted into the product, the mechanism can be started. First, make sure the Dmu Kinematics Toolbar is enabled. If it is not enabled, then go to View, Toolbars, and select the Dmu Kinematics Toolbar. Next, click the tool with the anchor symbol to choose a fixed part that will not move in the mechanism. Select New Mechanism and give the new mechanism a name. Now click on the part to be fixed. This is an important step as all mechanisms must contain a fixed part. This step also creates a mechanism under Applications in the tree. With a fixed part within the mechanism, the first joint can now be created by expanding the Joint tool, which is located above the Fixed Part button, and selecting the type of joint desired. In this example, a Revolute Joint will be used. When the Revolute Joint is selected, a new dialog box will pop up asking you to choose 2 lines and 2 planes. The line selected here will become the axis of the revolute joint and will create a coincidence constraint between the two parts. Select the axis of the peg on the base part and the axis of the hole in the handle part. The planes will determine the location of the two parts in relation to each other. This also creates an offset constraint, which can be controlled in the offset option. The null offset option positions the parts so that the planes selected have an offset of 0. This is the option that will be used for this example. Select the top faces of the handle and the base to be used as the planes. Creating this joint has added a revolute joint to our mechanism in the tree. Inside that joint are the coincidence and offset constraints. These can now be edited by double-clicking, which gives the option to change the way the joint looks and behaves. For example, changing the value of the offset constraint changes the distance between the two parts once the mechanism is updated. In the tree, we can also note that the number of degrees of freedom of the mechanism are displayed. In order for the mechanism to be able to be simulated, the degrees of freedom, or DOF, must be equal to 0. When working with complex mechanisms with many parts and many joints, eliminating all degrees of freedom can sometimes be the trickiest part. In this example, the way to eliminate our last degree of freedom is to add a driving command to our joint. To do this, double-click on the joint and check the box next to Angle Driven in the Joint Addition window. The limits of this new command can now be chosen in the Joint's Limit selection. The default here is from -360 degrees to +360 degrees, which means the joint will have a range of motion of 2 full revolutions. Click OK, and Catia will announce that the mechanism can now be simulated. Also, a command was created in the tree, and the DOF is now equal to 0. Now, the mechanism can be simulated to make sure it works the way it was intended. First, click on the Simulation with Commands tool to open the simulation window. With the Immediate option selected, you can drag the slider left and right to change the driven angle command and rotate the revolute joint. If the simulation option is changed to On Request, the angle can be changed, but the joint will not move until the play button is pressed. The mechanism can also be moved by clicking and dragging on the actual model. Before closing this window, it is a good idea to click the Reset button to reset the mechanism to the state it was in when the window was first opened. Now that the mechanism has been tested and it is clear that it works as intended, a real simulation can be created that can be saved and replayed. First, click the Simulation tool on the left and select the mechanism to be simulated. This brings up an Edit Simulation window and a Kinematic Simulation window. The simulation will be created based on frames that are added by pressing the Insert button and can be deleted or modified using the other buttons in the same row. The position of the mechanism at each frame creates an animation of the mechanism in action when played back. By default, one frame is added to the simulation from the beginning. To add another, move the mechanism using the slider in the Kinematic Simulation window, and then insert a new frame by clicking Insert. Next, change the interpolation step size to 0.01. This determines the size of each step created between the frames. The lower the number, the slower and smoother the animation will be. There is also a loop option, which can continuously loop the simulation, either skipping back to the first frame or by reversing the direction of the simulation once it reaches the end. At this point, the simulation can be changed and the frames can be added or removed to create the desired animation. When the simulation is complete, click OK, and a simulation is created in the tree. Simulation can be viewed and edited by double-clicking it on the tree. Next, if we compile the simulation, it will create a replay, which will save the simulation so it can be played as it currently is. First, select the Compile Simulation tool under the Normal Simulation tool. Give the replay a name, select the simulation to be compiled, and then select the desired time step, which is the same as the interpolation step size from before. Now, click OK and the simulation will be compiled, and a replay is created in the tree. Now, by double-clicking on the replay, it can be viewed using the same navigation buttons from before. The same loop options are also available, and the speed can be increased by 2, 5, or 10 times the original speed. Now, no matter what is changed in the simulation, or the mechanism, or the model, this replay of the simulation will always be there to view and will not change. Congratulations! You have now successfully created and simulated an assembly mechanism in Catia. At this point, be sure to save the product file. Now let's take a look at some other useful joints that are commonly used in creating assembly mechanisms. A prismatic joint is similar to a revolute joint in that it requires the user to select two lines and two planes. The major difference is that the prismatic joint involves a linear movement in one direction between the two parts. Therefore, it uses a length-driven command instead of an angle-driven command. A cylindrical joint is a combination of a revolute joint and a prismatic joint, which gives the user the choice to create a command that is either angle-driven, length-driven, or both. The prismatic and revolute joints it uses can be created on the fly or can be selected from existing joints. A rigid joint simulates the act of physically securing two parts together. This way, when one part moves, the other part moves with it. A point curve joint is used to guide a part to follow a curve. When creating this joint, make sure that the part contains a point that lies on the curve to be followed. This example shows a mechanism that uses two revolute joints and one point curve joint. A gear joint is a combination of two revolute joints, one of which is angle-driven, and which are connected by a gear ratio that is selected during the creation of the joint. A rack joint is a combination of a revolute joint and a prismatic joint. The rack joint can be angle-driven by the revolute or length-driven by the prismatic. Like the name implies, a cable joint can be used to simulate a cable or pulley type system. It involves creating two prismatic joints with a single command associated with one of the joints, which will drive the cable. With the information provided in this video, you can now explore the digital Markup Kinematics workbench and create your own mechanisms or add mechanisms to existing models. Here are some examples of what can be done using joint-based mechanisms.
In this tutorial, I will be introducing about rec joint and cable joint, starting with rec joint first. As you see in this demo, that in Catia, a rec joint is visualized as a gear turning while carrying the rec to translation movement. Now let's try to build a rec joint. We are in Dmu Kinematics Workbench. As you can see, these parts are already made. All we have to do is just apply the proper constraint to make it work. First of all, we need to fix one component. In this case, I decided to fix the rec support. As the pop-up windows show up, pick a new mechanism and name it rec. Then select the rec support. Now verify in the specification tree that you have just created a new mechanism called rec. Next, select rec joint from the Dmu Kinematics Toolbar. It is the third icon on the toolbar. If you don't see it, press on the little arrow and expand the Kinematic Joint toolbar, and it is one of the last ones. Since rec, it is the mechanism we want to create. There's no point of creating another one. We can also see that rec is composed of a Prismatic Joint and a Revolute Joint, and we need to create them. Assuming that you are familiar with the creation of Prismatic and Revolute Joints, I will breeze through this step. Create, match axis of translation, select the fixed plane, and OK. Do the same for Revolute Joint. Create, match rotating axis, fix the planes. One note that for the Revolute, it does not need to be coplanar with the select plane. It can be offsetted by selecting the offset and key in the value. The ratio is how much we want the block to translate per revolution of the rec wheel. I will set it 4 inches per revolution. So, key in 4 IN underscore TURN. Don't worry when you key in English units and it came back in millimeters. The value is the same, just how the Catia is programmed. The rec joint can be angle driven or length driven, and it refers to the driving parameter of this mechanism. In this tutorial, we select angle driven and left click OK. This is a good sign when you get this message. Before we start simulating, let's change the range of the driving parameter. Go to the specification tree under rec and left double click on rec.1. Change the lower limit to 0 and press OK. Left click on simulation with command and see if you like the results by dragging the command bar a little bit. I like the result. I will go ahead and close it. Now I have created a rec joint. Now let's see cable joints. As you can see, it is just 2 prismatic joints moving in the same direction along their planes. Let's try and build it. Again, the easy parts have already been made. Select fixed part, name the new mechanism cable, and left click on the support. Select cable joint, which is in the same toolbar as rec joint. Here you can see that we need to create 2 prismatic joints. As usual, create, line of translation, planes, OK. And for prismatic 2, it's the same thing. Create, line of translation, planes, OK. Use length driven for prismatic 2. What the ratio means is that if the ratio is 3, for every 1 unit of prismatic 1 translation, prismatic 2 will translate 3 units. Since our length driven is for prismatic 2, we will leave it at 1. Press OK. That's a good sign. Again, let's change the parameter ranges. Go to the specification tree, mechanism, cable, joint, and double click on cable.1. Change the lower limit to 0 and upper limit to 4. Select OK. Check our work again by simulation with commands. It works very well, so we can go ahead and close it. Choose Simulations from the DMU Generic Animation Toolbar. Highlight Cable and press OK. Click the 3 dots beside the spin box on the window and change the spin box increment to 0.25 and click OK. Select Automatic Insert from the Edit Simulation window. Now press on the arrow indicate up. Hold it until the value reads 4. Then press on the arrow indicates down until the value reads 0. This is a great trick to add frames to the simulation. Unselect the automatic insert, select the jump to start button on the very left, set the interpolation step to 0.2 and press play. Now we have a simulated cable joint. If you want to make it look more realistic, it is a good idea to add a cable and a roller just for a cosmetic purpose. In this case, I have a rect driven cable and it's still angle driven, and a cable joint that is driven by the rect. Therefore, neither option need to be selected. I also added a Revolute Joint served as a roller. Since we are trying to simulate multiple joints at once, simulation with laws is a better approach. Go into Formulas, filter type is time, highlight KinTime, change the name to a small t, and press Apply. Now filter type, select All, and select Angle 2. From the specification tree, we can tell it is the driven rect angle. Left click Add Formula, select Rename, and double left click on T. Multiply this value by 90 DEG divided by 1S. That is our angular velocity. Click OK. Do the same thing for angle, except using the angular velocity of 30.5. Now check the laws and you will see 2 formulas showing. Go to Simulation in the DMU Generic Animation. As you can see, our little trick wouldn't work if we simulate with commands. Select Use Law tab, go to the 3 little dots and change the time to 4s. Again, use Automatic Insert and insert all the times manually as shown. Unselect Automatic Insert and play. Now this looked more realistic. This would end our tutorial of rect joints and cable joints.
Hi friends, in this tutorial we are going to learn about the point curve joint plus slide curve joint mechanism. So right now I am in the assembly workbench. So I am going to show you this cylindrical will be sliding through these two curves. Now I've taken this line with the help of offset tool, which is available in the sketch workbench. So now I'm going to coincide with each other. I've kept a point and click on the line. Same for next also. Select the point and line. Control U. Then I'm going to digital markup Dmu Kinematics. Here we can do both the point curve plus slide curve joint mechanisms with the combinations. So now I'm going to fix the base. If you want, you can rename it. Just click on the base. Now I'm going to select slide curve joint. Here it is asking for curve 1 and curve 2. My curve 1 first will be this and curve 2 will be this. Click OK. Same, select slide curve. Same for this also, curve 1 and curve 2. Next I am selecting the point curve joint, curve 1 and point 1 it is asking. So I am selecting curve 1 and point as this. Click length driven, click OK. So here the mechanism can be simulated. Just closing this. Now selecting the simulation tool, click OK. Then just drag this one, insert, play in one direction, reducing the speed, play forward. So in this way you can create a point curve joint plus slide curve joints. For a basic understanding purpose, there are many videos which I have uploaded. Please watch that. So in this way you can create a point curve joint plus slide curve joint mechanisms. So I hope you like this video. Thanks for watching. If you have any doubt, you can comment on this video. Thanks for watching. Have a nice day. Bye. Hi friends, in this tutorial we are going to learn about the point curve joint mechanism. So right now I am in the digital markup Dmu Kinematics, where I have simulated these parts with the point curve joint and prismatic joint. So in this tutorial we are going to learn from a sketch to simulation process. So right now I am going to close this. In this method we are going to create. So I'm going to start with a new product. So starting with digital markup Dmu Kinematics. This is the top-down approach which I am going to create. So just insert, go to insert and select new part and click on the product. You will be inserting a new part. So open this tab and double click on the part 1. You will be shifting to the part workbench. So now I'm going to select a center rectangle. Will be of 200 length and the height will be of 150. Exit workbench, pair up to 10 mm. So now we need to sketch a spline. With the help of a spline we are going to create a curve. So we have created a curve on the surface. So now I'm going to shift to the digital markup Dmu Kinematics. So now I'm going to insert another part, new part. Just click on the product, click yes. So minimize, open this tab and double click on the part 2. I'm going to create a link 1 for here. this will be of 100 mm, and the distance will be 10 mm. Pad up to 10 mm. Reverse direction, preview. Okay, so now we have created a link 1. Now double click, shifting to DMU Kinematics, same new part, click on the product, yes, close this tab, open this tab, and double click on this, creating a new part here. So exit workbench. So now we have created a link to also. So now I'm going to place a hole on the surface so that the pointer can be fixed here. The dia for this will be 5 mm, and I'm going to constrain the edges. The height will be also 5 mm. So pocket. Okay, now we have created a link to also. Exiting the workbench. Same, now I am going to insert another part. Now insert, go to insert, new part, click on the product, yes, open the part 4. Now we are going to create a pointer which shall follow the curve continuously. So okay, the distance will be here, will be 100 mm, say up to 100 mm, and this will be of 2.5 radius. So the hole was 5 dia, so I'm given 2.5. Let's take 90 as it. So exit workbench. So now I'm using shaft to rotate at 360 degrees. So here it is asking for two things, one is the axis and another one is the profile. So I'm selecting the axis now. This will be act as the axis and the profile will be the entire one. Preview. Okay, so we have created a pointer now. So now we need to place a point on the pointer. Points is must, because it will be asking in a point curve mechanism, it will be asking to select a point. So place a point, go inside, exit workbench. So in this way you can place a point. So these are the 4 parts now we have created. In my next video I am going to show you this assembly and simulation process. Hope you like this video. If you have any comments, you can comment in this video. Thanks for watching. Have a nice day. Bye. Hi friends, in this tutorial we are going to learn about the point curve joint mechanism. Now in my previous tutorial I have shown you the creation of these 4 parts, and now we are going to start with an assembly design. So start, mechanical design, assembly design. So here the tools are not visible, so clicking on the product you can get it. So now I need to place this pointer inside this hole. For that I am going to select a coincide constraint tool, selecting the hidden line, and same for this, zoom, yes, Control U to update. So the second step will be the coincide of this pointer on this curve. select the point and curve, Control U, it automatically fits. So now the third step will be the contact surface, the base one and the link one. Control U to update. In this way you can create a assembly design. So we have arranged all the parts. Now in my next video we are going to simulation process. Thanks for watching. Have a nice day. Bye. Hi friends, today we are going to learn about screw joint mechanism in this tutorial. So right now I am in the assembly workbench Catia V5. So just I have imported these two components. This is a square head bolt and this is a square nut. I have used for these threads a square threadings according to the ISO standards. So right now I am in the assembly workbench. I have coincident these two components with each other with coincident constraint option. So now we are going to digital markup Dmu Kinematics, where we can do simulation process. So now I'm going to fix one of this component, screw joint. If you want you can rename it. Click OK. Just click on the component to fix the component if you want any one of the components. So I'm fixing on the screw. So here is the option screw joint, or you can go to alternate way, new joint, screw joint. Here it is asking for line 1 and line 2 in this dialog box. So here the line 1 and line 2 are the hidden lines of screw. So if you zoom it you can observe it clearly. Same process to this also for nut. Yeah, so clicking on the angle driven or length driven, any one of these you need to choose it. It's must. So I'm clicking on the angle driven. If you want you can click on length driven. So I'm clicking on the angle driven. So pitch I have taken as 1.75. This threading distance from one root to another root, it has been 1.75. Click OK. The mechanism can, if this dialog box appears, then your mechanism is successful. Let's do mechanism now. So I'm clicking on the simulation. Click OK. The value is very much low, so you can change the value to some -4000. Click OK. So insert, change the loop direction in one direction or a continuous loop. So here reducing the speed, play forward. In this way you can do screw joint mechanism. Hope you like this video. If you have any doubts you can comment on this video so that I can clarify your doubts. Thanks for watching. Have a nice day. Bye. Hi friends, in this tutorial we are going to learn about the roll curve joint plus slide curve joint mechanism. How we are going to apply for this simple mechanism. So in my previous tutorial I have shown you roll curve joint with Revolute mechanism. So there are a number of ways, so in that it's a second method. So right now we are going to apply for this. Right now I am in the assembly workbench, so I have imported these two components and I have designed these two parts in such a way that it should meet the parameters of the roll curve plus slide curve joints. And here we have at the edge of the cylinder I have taken the points same as to this also, so that it can coincide exactly to each other. So just coincide, take the click on the tool, go inside and click the points. You can get it. So Control U to update it. Next we are going to Digital Markup DMU Kinematics, where we are going to apply. So just I am fixing the component. If you want, you can rename it. Click OK. Now we are going to select the roll curve joint, or else you can go to Insert, Roll Curve Joint. So here it is asking for roll curve 1 and curve 2. Here I am selecting the curve 1. If you select in this way, it is selecting only line. So it is better to select here joint tangency position, so that it can select entire portion. Click on this and click on this sketch. Click on the length driven is must. Click OK. So next we are going to take slide curve joint, or else you can go to Insert also. Here it is asking for curve 1 and curve 2. Here also same. So select the tangency position and select the edge of the cylinder. Click OK. So the mechanism can be simulated. Click OK. Next go into simulation process. Simulation 1. OK. So here it is. The length is very much slow. So let's apply to some 800 highest. OK. Just insert, change the loop direction in one direction, reduce the speed, play forward. The mechanism with a simple roll curve joint. It's a basic idea how to apply the both. You need to, in this mechanism, you need to remember two things. One is the curve and another one is point. These two are important for the point curve joint, slide curve joint, roll curve joint, surface joint also. Points and curves are must to apply for this. Hope you like this video. Thanks for watching. Have a nice day. Bye. Hi friends, in this tutorial we are going to learn about the point surface joint mechanisms. This is the point surface joint mechanisms. So right now I'm going to show you from sketch design to how to apply a DMU kinematics simulation process. So I'm going to close this one. So let's minimize. So starting with a new digital markup DMU kinematics. So now I'm going to insert new part. Click on the part product. You will be inserting a new part. Just click on this part. You will be shifting to part workbench, selecting this spline, and I'm going to okay. Now I've taken this spline without any considering any parameters. So now I'm going to extrude. Extrude option is available in the geometric shape design workbench. So you can go to shift, you can shift to in that workbench. So now I'm using power input. So just give C and extrude, then you can apply here only. Now the dimension will be 40 mm and OK. So this is the part 1, and double clicking product, you will be shifting to DMU kinematics. So now I'm going to insert second part, same procedure. Just double click on the part. Okay, now I am going to select a reference plane, that will be a top plane, and this will be up to 150 distance. So okay, so okay, now this dimension will be say 400. and this one will be up to 30 mm. Okay, exit workbench, pad 20. Okay, so now I need click on the product, same procedure, insert new part. Nice, open this time, double click on the part 7. Now I'm going to create a on this surface a center rectangle, not be a rectangle. So this will be around 30, and this dimension will be also 30. So okay, exit. Now pad, reverse direction. Now I'm going to place a hole on the surface. Constraint, okay, don't know. Okay, the diameter of the hole will be 10 mm and the depth will be 20 mm. Okay, now we have created 3 parts in 3 different part folders. So double click on the part. Now I'm going to insert a last new part. This will be the pointer. So okay, now so okay, this now this will be, we have given for hole dia up to 10 mm, so the radius will be 5 and the height will be around 200, says 200. Okay, now using shaft, it will be rotating 360 degrees and asking for axis. Okay, preview. Okay, now I'm going to place a point. Why I'm going to place a point? Because in surface design, in a point surface joint mechanism and a point curve joint mechanism, slide curve joint mechanism, in this type of mechanism it will be asking to select a point, and if you want to coincide this surface and this only pointer, then it won't be coinciding with each other. So if you place point only, then only it will be coinciding with each other. So point is must. This is the basic rule of a point surface joint or any point curve joint mechanisms. So now I'm going to shift to the another. Now we are going to create an assembly design for this. So just select coincide constraint and select this point and this surface, Control U to update, and now I'm going to select same center axis, and for this hole, Control U to update. Let's make it some up distance for this. Okay, so now I'm going to shift now. Okay, in my next video I'm going to show you the simulation process. If you have any doubts, you can comment below this video. Thanks for watching. Have a nice day. Bye. Hi friends, today we are going to learn about the Revolute Joint mechanism in Catia V5 through DMU Kinematics. So right now I am in the workbench, assembly workbench. So I have imported these 2 components to assembly. Now I'm going to coincide. So before going to any mechanism, you need to arrange these 2 components in one direction so that it can be easily done in kinematics. So I'm going to Dmu Kinematics, digital markup, Dmu Kinematics. So where we are going to apply a Revolute Joint mechanism. So first of all, we need to fix a component. For any mechanism, the base is very much important. So I'm going to fix a component. If you want, you can change the name. Revolute Joint. Just click it on the component which one you want to fix it. So okay, next Revolute Joint, going for Revolute Joint, or you can go in alternate way, New Joint, Revolute Joint. So here it is asking for line 1 and line 2, so selecting the hidden axis and asking for plane 1 and plane 2. Here the planes and surfaces are same, so I'm selecting the surface. Here we cannot select a surface, so I'm selecting the plane. So clicking on the angle ring, giving offset distance 30, so that these two components should not be merged together. To avoid that, I'm giving 30 because I have taken this ball radius as 25 mm, 5 mm as a clearance. So to avoid merge, I'm giving 30 distance. So click OK. So here we can see the mechanism can be simulated. Dialog box appears. Click OK. Then we are going to apply a simulation process to it. Here we go, simulation process. Just rotate it forward, insert, change the loop direction if you want continuous loop or in one direction loop, or you can reduce the speed, play forward. The mechanism can be simulated with a Revolute joint. These type of joints are mainly used in door hinges, folding mechanism, and uniaxial rotations. So in another way you can also simulate this type of mechanisms. Just click it on applications, simulations, or you can go for Revolute speeds and accelerations, where you can go. Here it is asking for change at least one command value to start the simulation process. Okay, on request, play forward. In this way you can rotate in alternate way, speed and accelerations. So hope you like this video. In my next video I'm going to show you the prismatic joint mechanism. Hope you like this video. Please do comment on this video. Thanks for watching. Have a nice day. Bye. Hi friends, in this tutorial we are going to learn about the spherical joint, a basic application of the spherical joint simulation process. So right now I'm in the assembly workbench, so I've coincident these two objects, and now we are going to digital markup Dmu Kinematics simulation process. So first of all we need to fix a component, or else we can fix it later. So right now I'm applying a mechanism to it, spherical joint. So asking for point 1 and 2. So if you go to the part, there you can select a hidden point, you can observe it. So select it. Next, same process, select second point, then click OK. Now for spherical joint it is showing a 3 degree of freedom. So this 3 degree of freedom will be of rotational, Z, X, Y and Z axis. It will rotate. No translatory motion will be there in spherical joint. So now applying for Revolute joint. So asking for line 1 and line 2. So selecting hidden lines, axis 1 and 2. Next we need to select a plane. So I'm not able to select here, so I'm selecting from the tree specification YZ, and next second part will be XY plane. Clicking on the angle driven, click OK. The joint has already been defined. Okay, so I am fixing the component right now, so the mechanism can be simulated. Okay, fixing the component is must in any of this. So we are going to simulation process, applying mechanism 1. So I'm going to rotate, insert, changing the loop direction, continuous loop in forward direction, play. A simple mechanism of spherical joint. Most probably spherical joints are rarely used in universal joints. Hope you all understood this video. Thanks for watching. In my next videos I am going to show you the further application of rigid joint, fixing a component, complete fixing component, point curve joint, roll curve joint, slide curve joint. These are the mechanisms I am going to further upload. Thanks for watching. Bye. Hi friends, in this video we are going to learn about the cylindrical joint mechanism, a simple basic idea how to simulate a simple cylindrical joint mechanism. So right now I am in the assembly workbench. I have imported these two components. Now we are going to simulate these two components. So first of all I am coinciding these two components. Next we are going to another workbench, digital Markup, Dmu Kinematics, where we can apply a cylindrical joint mechanism. So first of all we are fixing a component for any mechanism. Base is very important, so we are fixing a component. So giving the name cylindrical joint, just clicking on the component, it will fix the component. So here is a cylindrical joint mechanism, or you can go in another way, new joint, cylindrical joint. So here it is asking for L1 and L2, so hidden axis of line 1 and hidden axis of line 2. So here we can select both angle driven and length driven. So cylindrical joint mechanism is a combination of both revolute joint, where we can give rotational, and prismatic joint is a transversal joint, so where we can move the component in linear motion in prismatic joint. So here it is in cylindrical joint, where we can give both angle and length driven. So click OK. So the mechanism can be simulated. Okay, it's a 2 degree of freedom. So right now we are going to apply simulation process to it. Okay, so first of all rotating and giving length to it, changing the value to -250. Okay, insert, change the loop direction, continuous loop, reducing the speed, play forward. A simple mechanism with cylindrical joint. In further videos I'm going to show you most intermediate stages videos in this tutorial. Hope you all like this video. In my next video I'm going to show you about the spherical joint mechanism and screw joint mechanism. Hope you all like this video. If you want to comment on this video, please do comment. If you have any doubts, you can mail me so that I can clarify. learning.practice.success@gmail.com. Thanks for watching. Have a nice day. Bye. Hi friends, today we are going to learn about the roll curve joint. In this joint we are going to apply a revolute joint plus a roll curve joint. So I want to rotate this wheel on this base, so let's see how we can do it. So right now I've imported all these components to assembly design, so I need to constrain this, or you need to keep it one direction. So right now I'm going to fix these components, so constrain these components, so clicking here, to the base. Okay, let's update. Now every component is arranged, so let's go to Dmu Kinematics, right? Digital Markup Dmu Kinematics. So here we can apply both the revolute joint plus roll curve joint mechanism. So first of all we are going to fix a component, giving the name roll curve joint. So I'm fixing this component. Now I'm going to select revolute joint, or you can go to new joint, revolute joint. So selecting the center axis, and tab. Okay, selecting this contact surface and this one. If you want, you can give a offset distance, angle driven. Okay, so the mechanism can be simulated. Okay, so next step, again revolute joint, clicking on the center axis, hidden axis, same procedure. Next, selecting the surface, clicking on the angle driven. If you want, you can click the angle driven, so again the mechanism can be simulated. Okay, so now we can see here we cannot apply, so I'm going to assembly design further and making a move. Okay, let's go to digital markup Dmu Kinematics. I'm applying once again revolute joint. So selecting the surface, selecting this surface. Okay, clicking on the angle driven. Okay, so the mechanism can be simulated. Till now it is okay. Now we are going to apply roll curve joint mechanism. So here is a roll curve joint, or you can go to insert, new joint, roll curve joint. So in this case it is asking for curve 1 and curve 2, so where we can select this line as a curve 1 and line curve 2 as this one boundary. Click on the length driven. So the created command has no effect on the degree of freedom, so okay, click on the OK option. So now we have all the elements, all the joints are constrained, so let's remove each and everything. So clicking remove this length driven, there are too many mechanisms to constrain it, so okay, once again you remove angle driven, the mechanism has too many comments. Okay, next removing another links. Okay, here it goes, the mechanism can be simulated. Click OK. So if you go in this way, you can get where you are making any mistake. If your joint is not correct, you can get noticed by this process. Now we are going to simulation process. Roll curve joint, click OK, insert, change the loop direction, reducing the speed, play forward, or you can go through one direction. It is a process of Revolute Joint and roll curve joint. Hope you all like this video. In my next video I'm going to show you some more advanced links. Thanks for watching. Hope you all enjoy with this video. Thanks. Bye. Hi friends, today we are going to learn in this tutorial about prismatic joint mechanism in Catia DMU. So right now I am in assembly workbench, so I have imported these two components. I have given contact constraint through one surface to another surface, this base surface. So this base surface can slide through this surface. So let's see how this can be simulated now. So right now we are going to another workbench, digital markup Dmu Kinematics, where we can do simulation process. So I'm clicking on, first of all we need to fix a component. For any mechanism we required a base so that the mechanism can be done. So first of all I'm fixing a component, new mechanism. If you want you can change the mechanism name, just prismatic joint. I want to fix this component, so clicking on this, just select prismatic joint, or alternate way just go to insert new joint, prismatic joint. So asking for line 1 and line 2. So here we can select line 1, in this case this edge, surface edge, and next asking for line 2 we can select this one. So here it is asking for plane 1 and plane 2. So planes and surfaces are both the same, so I'm selecting surface here and selecting this surface. So I need to slide this one through this surface, or else you can select this surface and for this surface if you want. It's your own choice. So clicking on the length driven is must. For any simulation process you need to click on length driven, depends upon the situation. So click OK, the mechanism can be simulated. So now we can simulate this process. Just close this tabs. Okay, prismatic joint. Okay, let's increase the value for this so that can be just insert, click on the loop direction, change the loop mode, continuous mode, and a one direction mode. If you want you can reduce the speed or increase the speed. Play forward in one direction. If you change it continuously it will come. So in this way you can select. These type of joints is used more oftenly found in hydraulic cylinders and pneumatic cylinders. Hope you all like this video. If you have any comment, if you want to comment any of this, you can comment on the video. So thanks for watching. In my next video I'm going to show you cylindrical joint mechanism. Hope you all like this video. Thanks for watching. Have a nice day. Bye. Hi friends, in this tutorial we are going to learn about the cable joint mechanism. So right now I'm going to start with digital markup Dmu Kinematics. So here I'm going to insert a new part. Just click on the product one, you will be inserting a new part. Open this tab and double click on the part one. You will be shifting to part workbench. So selecting the front plane and creating a sketch that will be a center rectangle, and now I'm going to give a distance of 200 mm and the height distance will be 150 mm. So exit workbench and padding up to somewhat 100 mm. This is the creation of first part. Double click on the product one, you will be shifting to Dmu Kinematics. So this type of approach is called top-down approach. Now I am repeating same procedure for creation of second part. So now I'm going to select this surface. Now I'm going to create a square block which will be going to slide on the surface. 30 mm, and height distance will be also 30 mm. So let's make it straight. Okay, now exit workbench. As this block will be sliding on the surface, and now I'm going to pad this. Okay, we have created two parts, and then I'm going to create another part, just repeating the same procedure as we followed first and second part creation. Selecting this surface and creating another part. So this will be of 30 mm, and height will be also 30 mm. So exit workbench, padding, reverse direction 20 mm. Okay, so now we created all the three parts. Now we are going to apply cable joint mechanism. So for that I'm going to fix a part. For every mechanism a base is required, and for that I'm going to fix a part. I'm renaming as a cable joint. Click OK and click on the part. It will be fixed. So now I'm going to select cable joint, or simply you can go to new, insert new joint, cable joint, prismatic joint 1 and 2. Here it is asking for, so select this create option, and here it is asking for four things. One is a line 1 and line 2. So select the edges, and same procedure for this block which we want to slide on this surface, and asking for plane 1 and plane 2. So select the surface and planes are both are same, so click OK. And here is second thing, so let's repeat the same procedure for this also. Click OK. So now here it is asking for ratio, so this ratio will be of 2, and I'm clicking on the length driven prismatic joint 2. So here the distance of this two prismatic joint will be covered twice when compared to this one, prismatic joint 1. It will move in a ratio, at a ratio of 1:2. So this will be of 1 and this will be covering at a distance of 2. So click OK. So here it comes, the mechanism can be simulated. If this dialog box appears, then your mechanism is successful. So now I'm going to apply simulation, cable joint, and simply dragging this and insert, change the loop direction, reducing the speed, play forward. So in this way you can create a cable joint. So hope you like. And what if you want to run these blocks between these edges? Then here it is, just create a line on this surface between these two edges, 1 and 2 edges. Then you can select that lines. I would like to show that one also to you. So in this way you can create a prismatic joint also. You can apply a cable joint for this process also. Just you need to create a line on the surface of this block only. Hope you like this video. If you have any doubts, you can comment below this video. Thanks for watching. Have a nice day. Bye. Hi friends, in this tutorial we are going to learn about the creation of point surface joint mechanism. So in my last tutorial I've shown you how to create these 4 parts and also applied a assembly design, and we have adjusted this pointer exactly on this surface. So now we are going to start with digital markup Dmu Kinematics. So now I am going to fix the part, so rename as a point surface joint. So select this surface, and now I'm going to select point surface joint mechanism, or you can go to simply new joint. Okay, this will be the point surface joint. So here it is asking for two things, one is the surface one and point one. So select the surface and point, click OK, and now we need to select a joint which has to move in this horizontal direction, so that it can cover this entire area. The pointer can cover this entire area. So that type of joint is prismatic joint. So I'm selecting the asking for line 1 and line 2, and planes and surfaces of both are same. So selecting, click on the length driven. Okay. So now we are going to apply a cylindrical joint. Why cylindrical joint? Means because the surface here is inclined position, so we need to, the pointer should move according to the surface. It should move in forward and backward by adjusting itself. The pointer should adjust by itself only. That type of joint is called cylindrical joint, where it can go forward and backward direction. Click on the angle driven. We have clicked already length driven, so click on the angle driven, click OK. So okay, now still we have not given, it is asking for degree of freedom 6. So for this surface and pointer we have applied a point surface joint mechanism. For pointer and this part 3 we have applied cylindrical joint, and part 3 and part 2 we have applied prismatic joint. So now we have not applied any kind of joint to this part 2 and the surface, so we need to apply a joint so that it should not move in any direction, but it should be fixed position. For that kind of joint we need to go to rigid joint. So part 1 will be the surface and part 2 will be this. Okay, so click on the mechanism. So now we are going to apply simulation. Point surface, click OK, rotate 360 and increasing the value 400, click OK, and now OK, just go to insert, change the loop direction, reduce the speed, play forward. So this type of joint is called point surface joint mechanism. So you can see here, according to the surface here, the pointer is moving. So hope you like this video. If you have any doubts, you can comment below this video. Thanks for watching. Have a nice day. Bye.
Hello, this is Mohammed Shakil here, and in this tutorial series I'm going to show you how you can work with the prismatic joint in the Dmu Kinematics in Catia V5. So I'm going to open up digital markup and Dmu Kinematics. So first of all, let me just create let me insert a new part here. Click on the product and double click on the part so that you get back to the sketcher workbench, part design workbench, and start doing some model here. just come out of the sketch and I'll do a padding for this. 40 more extend or 60. So now I'm going to come out of it, and right now I'm back at the DMU Kinematics workbench, and now again I'm going to insert another part. Click on the yes. So make sure your new part is not under this part and it's completely another part here. And now you're going to insert another part now. So this time you can use the profile tool. Okay, use the dimensioning. The last one over here, and now just break all the bones over here. That is a coincidence bones. Just remove all those bones here, so you're free to move anywhere. Now select the whole thing here and do the auto constraint here and click OK. And now select the whole thing here and drag this up somewhere over here, and just come out of the sketch and do a padding for it, so maybe around 20. So you have two parts right here. Now just come to the DMU Kinematics workbench once again, and now comes the kinematics part. So go to the new mechanism. You have inserted a new mechanism right here. Now click on the fixed part, make this fixed, then go to insert new joint prismatic. Right here you need to select the edges first and then the plane, and click OK. You can see it has aligned itself to the parameters which I've given. And now what I'm going to do, I'm going to go to the application, joints. Here you have joints. So do a little bit of editing in the prismatic, that is the length driven, just on the length driven, and once you click OK, you have this mechanism can be stimulated dialog box appearing. So right now you can simulate the mechanism. Now just click on the simulation with commands, and once that is done, just move your slider back to the initial position, and this is your initial position. Now just move your slider back to the final position, move it to the final position. Now just do a play, and you can see the simulation happening. So this is a simple simulation, prismatic simulation being done in the Catia V5. So if you want the movement to happen between these two limits here, then what you need to do is you just move it over here, and you just note down what is it, it's -40, and just move it over here and see what is the distance. It's 59, it's 60, so -40 and 60. Keep that in your mind. Go to the joints here, give -40, and here 60, click OK. And right now if you go to the over here, if you try to move it, move after that. So you can move it over here, you can keep it here, move your slider back to the final position, keep it over here, and just move it back, give a play, and you can see your slider, your prismatic joint working perfectly between the limits which I've specified. So I hope you enjoyed my video. I hope you I hope you're not having any doubts on this, because it's pretty simple. And if at all you have some doubts, you can comment just below my video and I'll be getting back to you as soon as possible. So I hope you enjoyed my video. Thank you. Hi, this is Mohammed Shakil here, and in this tutorial I'll be working with the Spherical Joint command, which is coming under the Dmu Kinematics Design Workbench in Catia V5. So I'll open up Dmu Kinematics, I'll insert my first part right here. So I'm going to do the first part sketch, so you can follow exactly the same method or the same dimensions and everything, whatever I'm working with. Come out of the sketch and do a padding of say 30 each on both sides. And now you're going to create a spherical hollow over here. So for that I need to insert a point at 0, 0, and at the point I'm going to insert a sphere which is coming from the wireframe and surface design workbench or generative shape design workbench. So you have your sphere created right over here. Now I'm going to insert surface base feature and split. Now I'll select the sphere and click OK, and the spherical portion is removed right here. Now my first part is ready. Now the next work is to create the next part. So the next part is being inserted under the same product. So make sure after you click on insert new part, you're clicking on the product and not under the part. And next insert the next part. So your next part is also going to be a sphere, and the sphere should fit inside the spherical hollow which you have created just before. So make sure you're giving the same dimension. So it should be a radius of 20. You do a shaft of 360. So you have your spherical surface being created. Now let me create a handle for this so it looks better. Fit all in. So you have your two parts ready for our spherical joint command. So let's work with the Dmu Kinematics Design Workbench once again. So the first step, as I said before, is inserting a new mechanism. Once you insert a new mechanism, you have a mechanism being created here. As there is nothing included, the degrees of freedom is 0. So now I'm going to fix a part here. So this particular basement is fixed, and now I'm going to go to new joint, spherical. So the spherical joint is used to joint two parts with its centers. So once a spherical joint command is being created on all the simulations, that particular two parts is going to share the same centers. So I'm going to show the software that these are the two centers which I want to mate with, and I'll click on OK, and it's going to come and assemble to the first part which was fixed. So you have your spherical joint command being created here, but still this cannot be simulated. It cannot be simulated because there are still 3 degrees of freedom for this particular assembly which you have done over here. So the 3 degrees of freedoms are 3 of them are rotation, and 3 of them are rotation with respect to X, Y, and Z axes. So for creating a simulation, the degrees of freedom should be according to whatever you require. So for this particular joint you need to add some more joints so that you can work with the simulation. So I hope you enjoyed my video. So if you want to do the simulation, keep watching, because I'm going to do few more joints for this, and I'm going to show you how you can simulate the model. So I hope you enjoyed my video. Thank you so much for watching, and subscribe me, like my videos, and ask me doubts, ask me for tutorials, and support me please, and thank you so much for watching. Hi, this is Mohammed Shakil here, and in this tutorial I'll be showing you how you can do the simple simulation for this particular spherical joint which was created in my previous tutorial. So I highly recommend that you watch my previous tutorial so that you'll be knowing how you can do the spherical joint command between these two parts. So if you have watched, then keep watching to know how you can simulate it. So let's see, you have two parts right here in front of us, and these parts are mated with the spherical joint. So we have 3 degrees of freedom, as you can see that under the application mechanisms. So let's see what are the 3 degrees of freedom which they are showing. So I'll go to the assembly design workbench, and I'll go to edit, move, manipulate, and I'll click on the with respect to constraint, and I'll click on X, it doesn't move, Y, it doesn't move, Z, it doesn't move. It means that it is not having the translation degree of freedom in 3 axes. Now let's see, it has rotation degrees of freedom. X-axis it has, Y-axis it has, and Z-axis it has. So it means that the 3 degrees of freedom which they are talking about over here and are the rotation of X, Y, and Z axes. So you need to create some joint so that the joint is going to allow this particular part to do the movements only in one particular axis or 1 degree of freedom. So for doing that, I'm going to come back to the DMU Kinematics design workbench, and I'm going to insert another part, insert new part under the same product, and that part is going to be a simple sketch. So as you can see here, it's a simple sketch, and now I'll invoke the Dmu Kinematics workbench, and now I'll go to the new joint, and I'll select I have selected the Revolute Joint, and you're selecting the Revolute Joint because you want this part to do the revolution with respect to only this axis. You're constraining this part from 3 degrees of freedom to 1 degree of freedom. So I'm going to show the 2 axes, 1 and 2, and the planes 1 and 2. I'll click on angle driven. Make sure you're clicking on angle driven and click OK. Still this assembly cannot be simulated because again you have 3 degrees of freedom. To constrain it once again, you need to go to insert and do a rigid joint between the part 3 and part 1 and click OK. And now you have the mechanism can be simulated dialog box right here. That means that your object is ready for simulation. Now you open this and double click on the speeds and acceleration, move your slider backwards and rotate your object maximum, and move it on the right side, rotate your object, and now move your slider back and click on play, and you can see the simulation happening. So this is how you can do the simulation for the spherical joint, and this is a simple method of doing the Spherical Joint Simulation in Catia V5. So I hope you enjoyed my video, and keep watching, keep subscribing me, liking my videos, and I need all your supports to keep uploading more and more videos. I hope you enjoyed. Thank you so much for watching. Hi, this is Mohammed Shakil here, and in this tutorial I'll be dealing with the Cylindrical Joint command, which is coming under the Dmu Kinematics Design Workbench in Catia V5. So for doing the Cylindrical Joint, I'll first open up the Dmu Kinematics Design Workbench and go to Insert, New Part, click on the product, and you'll get a part file which is under the product. And I'm going to create my first sketch here. I'll do padding for this, and I'll do the next sketch. So let me position the sketch here. Come out of the sketch and give a radius or diameter for this. Now I'm going to design my next part. So I'll give a slight a kind of profile over here. Now I'm going to do the cylindrical joint for this. So go to the Insert, first double click on the product so that you come to the Dmu Kinematics Design Workbench, and go to Insert, New Mechanism, and you have a new mechanism being created under the Applications menu. And now go to Insert and Fixed Part. So this is my fixed part, and now the next step is to go to New Joint and select the Cylindrical Joint and click on both of the axes here, and check on angle driven and length driven if you want both of the drive in the simulation, and click OK, and you get the window which says the mechanism can be simulated. That means you are successful in creating the cylindrical joint. Click OK, and now click on the simulation with commands, drag both of your sliders on the left side and move it on the one anterior position, and again move this back here and move this back over here. Now you can see the simulation. This is how you can simply create a cylindrical joint in the Dmu Kinematics Design Workbench in Catia V5. So I hope you enjoyed my video. Keep watching, and comment. Any doubts you have, you can ask me. You can comment just below my video, and I'll be getting back to you as soon as possible. Feel free to ask, and make my channel lively. Thank you so much for watching. Hi, this is Mohammed Shakil here, and in this tutorial I'm going to talk about the custom axis creation in the Catia V5. So I'm going to open up a part design workbench, and let me create some object here. So in my previous tutorial I've shown you how you can create custom axis in any required point of this particular object. So in this tutorial we'll be learning more about the custom axis creation. So let's go to the Insert, Axis System. So before watching this tutorial, I highly recommend you to watch my first part of this tutorial, so that you'll come to know about the continuation of this. So now I'm going to switch to the axis rotation here, and I'll specify one of the origin, and this is going to act as the origin now. Once I'll select, I need to show the software which one of the axes is going to act as my x-axis. So in this, I'll select this particular edge, and now I'm going to suppose to select the reference surface, so that with respect to that surface, a rotation is being done on the particular axis. So this tool is mainly used, this axis creation kind is mainly used when you need to specify an axis and you need a rotation to, and you know the correct angle with respect to which you want the rotation. So I've selected this as the surface, and now I'm going to specify the angle here. And once that is specified, as you can see here, an angular rotation is being happening over here. With respect to this particular surface, as you can see, with the z-axis, an angular rotation is being done. So we have few more options here. If you click on the z-axis reversion, the z-axis will come here, and x-axis reversion, the x-axis is gonna come here, and the y-axis, if you click on the y-axis, it will come here. So this is how you can reverse the axis also in this. So these are the options which comes in the axis rotation of the axis system definition dialog box. So I hope you enjoyed my video. Any doubts, any clarifications you have, you can comment just below my video, and I'll be getting back to you as soon as possible. So like my videos, and comment on my videos, and subscribe me, and keep watching my videos, and like my page in Facebook too, which you can see the address right somewhere over here. So I hope you enjoyed. Thank you so much.
This video tutorial will show you how to make a rack joint in Catia V5. Let me first introduce you to the parts that I'll be using to make a rack joint. This is a cylinder. It is very easy to make. Just make a sketch of a circle and then extrude it. Also notice this line, this individual line that is just above the cylinder. I'll show you later what this line means. Let us go forward to the second part. This is the sleeve that I'll be using. The internal dia of this sleeve is equal to the external dia of the shaft, and the external dia of this sleeve is arbitrarily 20 mm greater than the internal dia. Going forward to the third part. This is a plank. It can also be made in the sketch and then extruded. This will actually act like a rack in this rack joint tutorial, and the second part, that was the sleeve, it will act like a pinion. Now let me just assemble them. I hope this was not a difficult task. So these are the three parts that I just showed you. Let me just simply separate them from each other so that you can better see them. Okay, so now I'll just apply the constraints that are required. As I told you earlier that this shaft and this sleeve, they are just mounted on each other, and this sleeve has to be rotated about this shaft. So just apply the coincidence constraint between the axis of this sleeve and the axis of this shaft, and then apply the offset constraint between the face of the sleeve and the face of the shaft, and set it to 0 mm. Done. Now the next part is to just fix this shaft so that the sleeve can freely rotate on the shaft. Now our next task is to make this plank here on the top of the pinion, so that this plank, or you can say rack, will slide on this pinion surface. That's why I draw this line here, so that I can coincide this line and the edge of the plank with each other. So I just go to the coincidence constraint, select this line and the edge of the plank, and just coincide this. Now I go to this manipulator and this drag and rotate along any axis. I select this line and I just rotated this plank so that it could be on the top of the sleeve, and then I again manipulate and just simply drag it along the x-axis so that it could be on top, and I applied a coincidence constraint for the surface of this plank and the horizontal plane, so that this plane is fixed here and not going the other planes. So this is how we do assembly of the rack joint. Now let me go to the simulation part. I go to the Dmu Kinematics workbench. You can see here the workbench. Let me start with making a new mechanism and just fix this part. Now you can see here in the joints there are a lot of joints: Revolute Joint, Prismatic Joints. Let me go directly to the rack joint which is present here. This is the rack joint dialog box. It asks for a Prismatic Joint and a Revolute Joint. See, this rack has to slide over this pinion, so there has to be a Prismatic Joint, because this is a sliding only in the one direction and there is no other degree of freedom for this plank. And this Revolute Joint is because this sleeve has to be rotated about the axis of this shaft, and there is no other motion of this sleeve, so there has to be a Revolute Joint in there. So I created a Prismatic Joint. This line 1 and line 2, these are actually the lines that will be sliding against each other, or you can say the relative motion or the relative sliding will occur between these two lines. So let me just select the reference line and the line which has to be slided, and it asks for a plane, so just select me this plane which is the fixed plane or the reference plane, that is the top surface of the shaft and this surface of the plank which will be sliding. Okay, then revolute joint, as I told you, between the sleeve and the shaft. So I selected the axis of the sleeve and then the axis of the shaft, and then I selected the surface of the sleeve, then I selected the surface of the shaft. Okay, then as for a radius ratio, I selected the shaft. Okay, then there are two options present: length driven for prismatic and angle driven for revolute. You can select any of these two, but for better visualization, let me just select this length driven for prismatic. Okay, the mechanism can be simulated. It's a nice message. Simulation mechanism 1, and the command that we gave, the length driven to prismatic. So I just drive this rec and insert this value. I multiple loop it, select the velocity appropriately, and then I just play the simulation. You can say this is a simulation. This sleeve is freely rotating about the axis of the shaft, and this plank is just sliding along this direction on this sleeve or on this pinion. This is how the steering works. This is system engaged there. So this was the tutorial. Thanks for watching.